Welcome and thank you for joining. We'll take a look at another exercise from the textbook, page 84, number 28. Let's read the question first. So we have to sketch the graph y equals f of x and find an expression for f prime x. Indicate any points at which f prime x doesn't exist. As you can see, f of x is a piecewise function. The first piece is a first-degree polynomial function, or quadratic, and the domain of it is x less than 3. The second piece is another polynomial function, but first degree, or a linear function, and the domain is x bigger than or equal to 3. As you see here, both pieces are polynomial functions, different degrees, and we know that polynomial functions are differentiable for any real number x within their domain, which means that x squared will be differentiable at any x value less than 3, and x plus 6 is differentiable for any x value bigger than or equal to 3. Now, the point in question here would be x equals 3, because this is where one piece ends and the other one starts. So we know that there are two conditions for a function to be differentiable at a point. Condition number one is that the function must be defined at the point, which means that f of 3 exists. Condition number two is that we're able to draw a tangent, and the slope of the tangent should have a measurable value. So in other words, we're going to say the slope of the tangent is defined. So the fact that f of 3 exists, it means that we can draw a tangent, but then the slope of the tangent has to be of measurable value. Now let's take a look at the function f of x and see if the function at 3 exists. So if the function is continuous, in other words. So there are three conditions for continuity. Condition number one for continuity is that the value of the function at 3 must be definable, or f of 3 exists. As you can see, x equals 3 is part of the second piece in the equation of f of x, which means that to find the value of f of 3, we need to use y equals x plus 6. So that means that f of 3 will be 3 plus 6, or f of 3 equals 9. Condition number two is that the limit of the function when x approaches 3 from the left must equal the limit of the function when x approaches 3 from the right-hand side. On the left-hand side, we have x squared. So what that means is that we're finding the limit as x approaches 3 from the left by using the equation y equals x squared. So using the function x squared. And the right-hand side would be x plus 6. So for the right-hand limit, we have to use x plus 6. So if you substitute x by 3, here we're going to have 3 squared, or 9. And if we substitute x by 3 in the right-hand side limit, we'll have 3 plus 6, which is again 9. As you can see, the limit on the left-hand side of 3 is equal to the limit on the right-hand side of 3, which means that the limit at 3 exists. And it is equal to 9. As you can see, and we have arrived in condition number 3, the value of the function at 3 equals the value of the limit at 3, which makes this function continuous at 3. So therefore, we're going to say the function is continuous at x equals 3. So this is the algebraic explanation of how the function is continuous at 3, which means that we can proceed with finding the derivative. In the question, we're asked to graph this function. So we're going to try to sketch the graph of this function down here. So we need a big vertical axis because we have the y values for the first piece go all the way up to 9. And the first piece, I'm going to highlight this in pink. Oopsie. Would be the function y equals x squared. At x equals 3, we'll have the value of y equal to 9. So 3, 4, 5, 6, 7, 8, 9. So 3, 9 will be an empty circle, obviously, because x equals 3 is not part of the first piece. And now all we have to do is draw the parabola y equals x squared. So remember that we draw the parabola starting from the vertex, over 1 up 1, and then over 1 up 3, over 1 up 5. So this will take us all the way up here. And then we do the same thing on the other side, over 1 up 1, over 1 up 3, over 1 up 5, and then we stretch the other arm. So the next piece is y equals x plus 6. This is a linear function with a y-intercept at 6. So 1, 2, 3, 4, 5, 6 in here. And this line will have a slope of 1. So 1, 1, which means that according to the domain, specified domain here, we're starting at x equals 3. And at x equals 3, this function will be defined. We have to fill the circle in because we have the value of x equals 3 included on this equation. And from here on, we draw the graph of the line with a slope of 1. And this will be the second piece. As you can see, the function actually is continuous at 3, as we proved it algebraically as well. And that's because there is no hole in here. So we continue drawing the graph of the function, and there are no breaks on the graph. Now, the question that we're asked is to find the derivative. Now, in order to find the derivative means that we have to find the derivative of each piece and see if the derivatives are the same. If the derivatives are the same, then we can conclude that the derivative exists. So if you want to find the derivative of the first piece, then we're going to say that f prime of x for x values less than 3 would be equal to the derivative of x squared. The derivative of x squared is 2x. For the second piece, which would be f prime, again, this would be on the left-hand side, we can call it, and this would be on the right-hand side, if you wish. And for the second piece, we'll say that the derivative will be the derivative of x plus 6. The derivative of x plus 6 is the derivative of x, which is 1, plus derivative of y, of number 6, which is 0. So the derivative will have a value of 1. So if we were to measure the derivative at x equals 3, then we're going to say that on the left-hand side, f prime of x equals 2x, which means that f prime at 3, and we're talking about the left side, would be equal to 2 times 3, or 6. If we were to find the derivative on the right-hand side of the point x equals 3, that would be equal to 1, and we don't even have to input the value of 3 in here because this is the derivative with a value of a constant number. So this derivative has a constant value. So therefore, we're going to say that the derivative on the left side of number 3 is positive 6. On the right side of number 3 is equal to 1, which means that we do not have a definite value for the derivative of this function at x equals 3. And as you can see in here, if you were to draw the tangent line right at x equals 3 following the parabola, then you would see that the tangent line will be going this way. It will have a very steep slope. I'm going to have to grab this. There we go. And for the second piece, you see that the steepness would be equal to 1. And that means that the derivative at x equals 3 for this particular function does not exist. I hope this made sense, and thank you for watching. Bye for now.